All right. So a slope field in our topic of differential equations can also be called a gradient field or a direction field. We can only draw them for a first order differential equation. So we need to have the y dash as the subject, and it will be written in the form y dash equals, and it says g of x comma y, meaning it will be some function of x and possibly y. It could be both of them. It could be one or the other, and you'll see the difference when we do a few of these. How to draw a slope field. For each point on the coordinate plane where our g of x, y is defined, the solution curve has the gradient given as y dash of g of x, y. Choose a suitable grid of points in the coordinate plane, and we need the x and the y values. Draw a table to show the gradients at the chosen points. Display these gradients by short tilted line segments of a fixed length centered on these grid points in the coordinate plane. And this is what takes time, and unfortunately it is not very accurate. The resulting diagram is called a slope field or a gradient field or direction field. So here is an example of a slope field. Consider the differential equation. We have y dash equals half x. We're choosing the grid points. This table's been done for us, which is lovely. So all you do to get those points, though, is you're subbing in. We only have x on the right-hand side of that equation that I've, this one here, this equation here. So you're subbing in, first of all, that x is equal to -4. And if you go half times -4, you get the -2. That's how they get these values that are in here. And then you fill in that whole table, and then you have to painstakingly sketch the gradient of each one of those points. So this point that I've just worked out here, this -4, 4, you go over to your Cartesian plane, you go to x equals -4, which is here, and then down to y equals 4, which is this line here, right? Oh, thank you. Yes, you're right. I want +4, that one up there. So the gradient of that line is -2, and you've got to try and draw a -2. And the reason it gets difficult is because if you look across those gradients there, you've got -2, then -1.5, -1, -0.5. It's pretty hard to tell those gradients apart when you're trying to sketch them, but you just do as best as you can, and you're trying to kind of show that it's going from a steeper gradient, it's getting down to 0, and then it's going back up to a positive gradient again. What we're doing is, remember that our differential equations represent a family of curves, right? So this is showing us what the family of curves could look like, right? And that can be seen down here. So it says down here, the slope field, the diagram suggests a family of parabolas that each have a turning point at x equals 0. Because you can kind of see here that all of these curves, they kind of have a gradient of 0 in here, and then they're all kind of getting steeper on the sides from there, right? Each parabola has a vertical translation of each other. So you could do another parabola up here, and you'd have all these different families of parabolas going up or down from the origin, right? And you can also check that with your calculus. Whoops, that wasn't meant to happen. Here it comes. So our differential equation was half x. If we integrated that equation, you add 1 to the x, which is x squared over 2, and it would become a quarter x squared. So the quarter x squared, you can see that it's a parabola. Quarter is just changing the steepness, but it's the plus c on the end that indicates it's a family of parabolas that could be anywhere moved up or down on that Cartesian plane. All right, so yes, it's a little bit of a painful topic, but unfortunately this is a new thing they've added into the syllabus that we have to do. Okay, so question 1, construct a slope table for the differential equation y dash y plus x equals 0. Now, first of all, remember what I said. If you're going to fill in a table and draw this thing, you need the y dash by itself and everything else over on the right. So I have to rearrange that equation. So first of all, y dash y, move the x across, would equal -x. And then divide by the y, you would get -x over y. Now here comes the fun times. We have to substitute all the points in that table into that differential equation. So first of all, x is minus 4, y is 4. So I'm doing in that equation, I'm doing minus 4, so plus 4 over 4, which is 1. Do we need to use a calculator? No, we're good. All right. So let's do the next one. I'm going to move across. I'm going to do the whole top line. So I'm going to go to minus 3 for x and 4 for the y. So the minus will always cancel out with the minus in the formula, and it's just going to be 3 over 4. What's the next one going to be? 2 over 4, or in other words, a half. The next one's going to be 1 over 4. 0 over 4 is just 0. Now we have the minus in front of a positive number, so it'd be minus 1 over 4. And then minus 2 over 4, which would be minus a half. Minus 3 over 4. And then minus 4 over 4 would be negative 1. That's just the first row. Move down to the next row. We're going to be minus 4 and now minus 3. You already love this section? Yeah, me too. All right, so minus 4, the minus will cancel out with what we're subbing into, so it'll just be 4 over 3. And then 3 over 3, which is just 1. And then 2 over 3, 1 over 3, 0, negative 1 over 3, negative 2 over 3, negative 3 over 3 is negative 1, and negative 4 over 3. I know it's slow, but is it making sense how I'm getting these numbers? Good, all right. See if you can fill in the rest of the table. Yeah, we're going to do the whole table. Now, when you get to the 0 line, you are doing whatever number minus 4 divided by 0. Can you divide by a negative sign? No. So these are going to be not possible things. Putting little stars in here. Can't divide by 0. It's not equal to 0, that's right. There's no possible solution for that. Then down to the negative ones. The good news is that when the negative one, the value is going to be the same as positive one. It'll just be the opposite sign. So it'll be negative 4, negative 3, negative 2, negative 1, 0, positive 1, 2, 3, 4. And the negative 2 will be the opposite sign of positive 2. Ben? Yeah. All right, how are we going? We almost there? Okay. From that table, we now have to draw a slope field down here, and there's no grid there. Does anyone else want the ruler? You only need the ruler for the Cartesian plane part, not for the... Do you need one too, Sandy? No. You got one? Okay, so we need to do a four all the way around, right? So from the origin, plus 4 to minus 4, both x and y. So when I did mine on my booklet, I could fit it in if I put it right over here on the side. And I did a centimetre for each space. If you do half a centimetre, that's fine, but just remember you've got to try and draw these little gradients in there. You don't want to make it too squashy. On this line, there's no arrows on the slope field. Okay, half a centimetre if you have to. Okay, all right, so to draw them in, maybe you want to start with the 0 in the middle. So when y was equal to 0, we had all those stars in there, meaning we couldn't get a solution. What does that indicate in terms of a gradient? More than that. Thinking of our good old-fashioned rise over run, when is a gradient undefined like that? When it's horizontal is 0, vertical. Okay, so that means these are all little vertical lines at -4, -3, -2, -1. 0 is a bit tricky. 0, 1, 2, 3, 4. There we go. All right, because an undefined gradient, remember rise over run, is when you're trying to divide something by 0, which is a vertical line. Okay, now above and below that, so let's do the positive one. We have a 4 slope, positive 4, which means we need a very steep gradient of 4. And as I come across, it's going to get slowly less steep. That's a good English word, but anyway, shallower. As I get to x equals 0, it will be horizontal because it'll be a 0 gradient. So gradient of -3, -2, oh, sorry, positive. I'm not positive. They're positive, not negative. Positive, and then 0. A gradient of 1 should be still 45 degrees though. Okay, the other ones are just much steeper than that. Then as I go to the right-hand side, then they're all negative sloping. So I want a -1 slope. Then they're going to be getting steeper. The bottom, the -1, is going to have the opposite sign. So we're going to be starting with -4 gradient. So very steep negative gradient. -3, then -2, and then -1 will be our 45 degree, 0, and then +1, +2, +3, +4. I don't know how you tell the difference between those +2, 3, and 4. They just look steep. That's what I mean, not accurate. We are. Good job. Okay, so keep going. Now we want to go to 2. This gets even vaguer. So at +2, we're starting with a positive gradient of 2. So slightly steeper than our gradient of 1. Then 1.5. Then 1. Then half. So it's shallower. 0. -0.5. -1. -1.5. And -2. Ooh, try and keep them. That's mine's a little bit wobbly there. You've got to try and keep them all in nice lines as they come across. Then do the -2. So y equals -2 starts with a gradient of -2. Then -1.5. -1. -0.5. 0. +1, half, sorry, that should have been half, not 1. Half, 1, 1.5, 2. And keep going. So at 3, these gradients are getting closer together. So 4/3 is a bit over 1. Positive. Then 1, third, 0. Negative a third. Oh my gosh. I know. What?
Why, miss? Are these questions on the HSC very often?
We need to look at some. We'll have to have a look at some HSC questions. So the odds of them making you draw one, hopefully, is pretty small because it's just a huge chunk of time to waste drawing one of these. But unfortunately, the exercise does have quite a few of these. What?
It's so.
Yeah. Negative 1, 3. Oh, did I miss 1, 2, 3? No, 4 is this flat one. 1, 2. No, yeah, you're right. I did miss one. I did miss a. What did I need in there? A what now? There you go. Just another flatter one in there. Are you just copying mine? You shouldn't be copying mine. You're meant to be drawing these, but thank you for finding it. Okay, then -3. I was doing that line. Then 4, last row, starts with a gradient of 1 and just gets shallower, shallower, 0, shallower, 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 0. And then getting slightly steeper on the other side.
Will we be marked back?
As long as you can see the general pattern of what's happening. I'm not going to sit there and go, no, that is not a gradient of 1.5. How dare you?
I just love
It is. Okay, all right. So once we've got our slope field drawn, as, who was it? Was it Isaac? Said, you can see that's kind of making a circular pattern in there. So part C says, what family of curves look as if they are the solutions to this differential equation? It's circles. You can see that you've kind of got it flat at the top, flat at the bottom, and it's curving around the sides, right, of all of those as you come out from the origin. And I guess that does also say the center of that circle would be at the origin, with center at the origin. Check your conjecture, because we've made a prediction here of what we think. We think it's a circle. Check this by differentiation. What is the equation of a circle with a center on the origin? Our general formula that is.
plus y squared equals.
Well, we say r squared. X squared plus y squared equals r squared. Now, we're checking by differentiation. To differentiate that, I am going to have to use the chain rule that I talked to you about last lesson, because I'm differentiating in both x and y there. So differentiating 2x, that's the easy part. Oh, sorry, I said the answer. Differentiating x squared is the easy part because you get 2x. You bring the 2 down the front, x, subtract 1 from the power. It's the y squared that's a problem, because if we're differentiating with respect to x, what do we do with a y? Look back in your notes. How do you differentiate a y squared? There was 2 rules that I gave you. One was, yes. One was for differentiating a y squared and one was for differentiating an xy. Okay? Then no, because when you differentiate a constant, because r is a constant, what do you get? 0. Okay, now if you divide everything by 2, you just get x plus y dash equals 0. Look back to the top of the page at the original thing that we were given. It was around the other way. It was y dash y plus x equals 0. Okay, good. Yep, well, not yet. We will, but not yet. Okay, so let's read through this. Summary of sketching a solution curve or integral curve. This is, and as we just discovered, not an accurate procedure. And sometimes it is not clear what curves there are. It is not like joining dots. It's not a dot to dot where you're just connecting things up. There's slopes. Sometimes there's asymptotes in there, and that can be hard to find what's going on. The purpose is to get a global view of what is happening before doing any detailed calculations. Apart from some strange singularities, two solution curves can never cross because the gradient at each point can only have one value. So that's something to keep in mind, that they won't be crossing over. An isocline, remember that word, is a curve. No, I'm saying you need to remember that name, sorry. An isocline is a curve that passes through points where the tangents have equal gradient. And we're going to be seeing some of those in the next couple of examples. In a slope field where the isocline passes through all the points where the gradient is 0, then every solution curve has a stationary point where it crosses the y-axis. We're going to see this in not the next example, but 2 more examples in. If you are given an initial condition such as the origin, start there and draw approximate curves in both directions as far as the restrictions allow. If there is no initial condition, draw at least 3 representative curves at different places on the plane. 2 solution curves can never cross. We said that before, apart from some strange singularities. Okay, so we're not going to worry about those right now. A is the answer? You're actually correct. The question was, which of the differential equations are possibly graphed in the diagram to the right? This is a multiple choice question, something you might get on your HSC. Remember, there is some multiple choice on there. So, how did you do that, Isaac? Or did you just guess?
I simply it couldn't be D, and then I looked outwards and I saw that for an x squared to be negative, like that had to be swapped around, and I didn't pay basic logic. But
Educated guess, but hard to explain.
I knew it was A. Like,
Yeah.
it was, it's basically
All right, let's get distracted. Let's not get distracted. All right. So what you want to do is you want to check the solutions by testing different points around your Cartesian plane. Okay, so if I'll start with the ones that don't work, and we can see why these ones don't work. Let's start down the bottom and work our way up. If we have y dash equals minus x minus y, one of the things that you notice about that slope field is that the vertical line there, the y, they are always 0. The gradient is 0 on that y-axis, right? It's always flat. So that means to get a gradient of 0, that means that you're going to have to you're going to have either x or y is equal to 0 all the time. Like, that's not going to happen, right? For different, like if it happened once, it'd be okay, but to have all of them, it's not going to happen if you've got 2 things that are subtracted like this. So let's try it with another one off the point then. Let's try it for, say, the point 1, 1. Actually, that's not a good point because that one looks all right, almost. 1, let's try negative 1, 1. If I sub in x equals negative 1, if I subbed in x equals negative 1, this point here, x equals negative 1, y equals 1, I'd get minus minus 1, which is 1, minus 1, which would be 0. Does that look like a gradient of 0? No, so it can't work. All right, let's look at the other 2. Boys, don't be silly. Y dash equals x minus xy squared. I'm going to C here. Again, check a different point. Let's check all these ones as we go around here. So if I do 1, 1, 1 times 1 squared is still 1 with a minus sign in front of it. It could work in the first quadrant. It looks okay there. The second quadrant, if I subbed in negative 1 times 1 squared, that would also give me a negative 1, but with the minus sign in front of it, positive 1 again. Still looks okay there. Check the third quadrant. If I do negative 1 minus minus 1, so 1, yeah, because there's minus in front of it. Sub it in. Let's try the third quadrant. Minus minus 1, that's a positive 1, times minus 1 squared. Do I need to write it down? Is that going to make it easier? All right. This one that I'm subbing in here, this green point here, I'm testing at the moment. So if I'm putting it into part C here, I've got minus, the x value that I'm subbing in is -1, and the y value that I'm subbing in is also -1, but I've got to square that. So that becomes a positive, that becomes a positive. The whole thing would be a +1, right?
Yeah.
Is that a +1 slope there? No. So it falls down in the third quadrant. The other quadrants all work, but it doesn't work in the third quadrant. I didn't check that one. You might be right. What about part B? You'd be checking the quadrants again, and I believe that one doesn't work in the second quadrant. Let's check it for the second quadrant. If I subbed in minus, then x is -1 squared times by 1. So the -1 squared is 1, but with the minus in front of it, it should be a -1 sloping gradient, and that's a positive gradient there. So it does not work in the second quadrant.
And then we did have the last one.
I did check it, but I was doing it in my head, which was getting you guys confused.
I was reading about
Oh, A. Yeah, you
Yeah.
check A, absolutely check A as well. So you could check, you're going to times the two x values together, and then the minus will change the sign. So if you go 1 times 1, that's 1. -1, yes, that's a -1 slope in the first quadrant. In the second quadrant, you go -1 times 1, which is -1. With the minus sign becomes a +1. Yep, that's a +1 slope. Check the third quadrant, check the fourth quadrant, and it'll work for all of them. Yes? It gets easier the more you look at them. You get used to subbing stuff in and seeing if things are sloping in the right direction. Okay, let's move on to question 3, which I think some people have already started. We now need to fill in another table and draw another slope field. This time our equation is y dash equals x plus y, which means as you're filling in the table, you are just adding the x value with the y value. So it's -4 plus 4, which is 0, and -3 plus 4, which is 1, -2 plus 4 is 2, -1 plus 4 is 3, 0 plus 4 is 4, 1 plus 4 is 5, 2 plus 4 is 6, 7, and 8. Yeah? All right, fill in the rest of the table. Yeah, the good news is that they do just count up as you go across the line. So you work out the first one, so -4, I'm doing the third row now. -4 plus 2 is -2, then it's just going to be -1, 0, and so on. Yes. So how on earth do you tell the difference between a -4 gradient and an 8 gradient? They're just both very steep gradients, right? Yeah, almost vertical, but they shouldn't be quite vertical. Be encouraging. Okay, so this time I have given you a little grid to work with. Sorry, I'll slow down.
No, it's fine. Just
Okay, so just as you go across the line, it's getting steeper and steeper and steeper. The first row is starting from a 0 gradient, so flat. Then 1, you're 45 degrees already at 1. And then steeper, 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 getting very steep. Not quite a vertical line by the time you get to an end. Once you get the negative gradients though, maybe you could go through and put all your zeros in. You have zeros coming down this diagonal here. You've got negative gradients to the left of those zeros. So I need a -1 then positive 1, and then from the positive 1 onwards, we're getting steeper again. And third row, -1, -2. Positive 1, positive 2, getting steeper.
I love this so much.
As long as it makes sense, that's the main thing. Okay, so I'm up to -1.
Got 'em. Damn.
And it's just. No, that's because.
That just kind of look like one of mine, doesn't it?
It does indeed.
I'm not gonna force the game left is just one dot in each row, then two games for the row.
Like the dots.
Yeah, connect the dots to make it easier. One, this is my favorite piece. Like this upside down steroids. It's going down.
Avoided.
Okay.
Very accurate. I'm joking.
Not accurate
Just
enough, hey Ashton. I need to get out there and calculate my rise over run.
In your graph, one of your lines is like flatter than the other two in between it.
Which
Is that
one?
just an error?
Which one?
Bottom line, third from the left.
Third from the left on the bottom row.
Third right.
You're talking about the very bottom row, the third one in. It's just not quite steep enough, right? All right. Okay. Thanks. Yep. Okay.
On the two one.
All right. Thank you. I'm very glad that I had you guys to critique my work.
If he's critiquing your work badly, then
Shouldn't look at yours. Not now. We're still doing this. All right. So sketch the representative curves, including the solution curve, through the origin. What you will notice is that we have those gradients of 0 coming down that diagonal, right? So you got, draw it. Different colors. Here we go. So down this horizontal, this -1 gradient going through the origin, all of those gradients are a gradient of 0. So it's saying that is, it's said in that word there that is a solution to the curve because they're all gradients of 0. So I'm going to draw a dotted line going through there in green. There is another interesting thing that you can hopefully see in this slope field is that if you go just one space down from there, all of those ones that I'm going through now all have a gradient of -1. Yeah, cool. So all those ones there with a gradient of -1, that is what we're calling, that's an isocline. They all have the same gradient. They all are going through those points. So I'm going to do another color for that one. Let's do the blue. Sorry, you don't have to do colors, but this way I can say the blue or the green. Okay, now what is going to happen? They're two of the line. They're the ones that are making lines, right? But what is happening with the rest of the curve? And remember that the rest of the solution curves won't cross over. They shouldn't touch each other. The one that I've done in green, when I read through the notes, I said if there is a solution curve when we have gradients of 0, that is going to represent the stationary point, because remember stationary points are when the gradient is 0, the stationary points of any curves going through it. Okay, so I need more colors. Where's my colors? I'm going to change that one to purple. this first zero here, as going through the origin, as I go to the left from there, I have got gradients getting quite steep, and they'll be coming up and they'll be approaching that line there. As you go to the right, look how steep those gradients are getting. They're getting steeper, 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 steeper. So this one's going to be going quite quickly up this direction. Okay, so that's the kind of curve we're talking about. You could have another one above there. So it's not a parabola though, unfortunately. It's not symmetrical. You would have another one up here further through this zero, so coming steeply up this way, and then it would be coming in close to that one. Or you could even go down to this zero down here and have steeply coming this way, and then coming in and kind of tucking in under those ones, not touching. Right, so that is what is happening on the upper side of that blue line that I've drawn there. What is happening below it? All of those gradients below are negative sloping gradient. So we know they're going to be decreasing curve. They're not equal in gradient. They're starting off, when you're near the y equals minus x line, they are quite, the shallowest they are there. They're at -1, and they're going to be getting steeper the further we move away to the left. So, for example, they could be coming up like this. Oh, that wasn't very good. Let me delete it. Don't want to have to delete all my other ones. They'll be coming up and getting close to that one that way. Yeah. So you'll have a bunch of curves coming up like that.
So that line is literally just an asymptote.
Well, it is actually a solution to the curve, though. It's not an it is a possible solution to the differential equation, but it is the one that's making a straight line. The green one is the gradients of 0, which is telling us where the turning points of those ones on the upper side of the line were.
Needs to breathe that combo.
Okay. All right. Question, that was part B, where I was trying to draw some solution curves on there. I did do the one going through the origin as I was asked. Part C, it says to identify all the isoclines of the slope field. The isoclines are the things that have the same gradient. So we notice that everything that has a gradient of -1 was where we had an isocline. So every line with gradient -1 is an isocline. Not that I haven't heard of them coming in yet.
I can't wait, actually. I'm really excited.
Focus, please. What would be the equations of the two lines that we drew that have gradients of -1? First of all, the green line going through the origin, y-intercept of 0. So it would be y equals -x. Right, that would be the green one. And we also had the blue line that I drew, which was moved down to a y-intercept of -1. So what's its equation? That's right. So there's the two equations of the two isoclines that we found in that slope field. And it kind of gives it away in part D and E here, because now it talks about them. It says part D, explain the significance of the isocline y equals -x. So that was the one, the green one, going through the origin. What do we know about that? I said it a couple of times. The zeros there indicate the stationary points of all the curves that are going through it. So this is how I wrote it down. Every curve that crosses the isocline. No, isoclines are straight.
So you can't have all the zeros.
You might have, you could put, I don't know, I'd have to have a think if you could actually get a curve that had gradients of 0 forming a parabola or a cubic or something, but it wouldn't be called an isoplane. Yeah. So it has a stationary point. I need a smaller texture, I think. There's two. There's two of them. That's why I've written down two equations. Every curve that crosses the isocline y equals minus x has a stationary point at the point of intersection. I think I should just use a different color. That pen's too thick.
Yeah.
Is that better?
Yeah.
Okay, so we knew because there was the zero, that the zero part, we knew that they were the stationary points. But the part that I've written in green in there is that we also could tell that these would be minimum stationary points because we had negative gradients on the left and positive gradients on the right. So that means coming down, 0, positive, right? Okay, what about the significance of our other isocline, the y equals negative x minus 1? Okay, so first of all, it is a solution to the differential equation. If you substitute it in, it is a solution. It is a line with equal gradients across the slope field. No other curve crosses that line. And we have two types of curves on either side of it. So it's kind of dividing the graph up into the two types of curves on either side. Where the curve that we're drawing, when it intersects with that 0, that's where the stationary point is. So the 0 was at the point -4, wherever plus it was, that is where the stationary point is. Correct. Yes. All right, so I just listed off about 4 different things that we know about that isocline. Let's write them down. So, the lines.
But everything was straight line then, isn't it?
No, there was 2 straight lines, everything else was curves.
That's almost your begin afterwards. What was the
Differential equation. Oh. No, I wasn't trying to be aggressive. Knock it off, you two. All right, so that's a whole bunch of stuff. That isocline is a solution to the differential equation. It is a line that has equal gradients the whole way across the field, so everything was -1 the whole way across. No other curve crosses that line, and we have 2 types of curves, so one on either side of that line. Other curves are asymptotic, so it's behaving like an asymptote, even though the other curves are asymptotic to it, but it is actually still a solution. Typically, we think of an asymptote as being values that don't exist, we're approaching, but it is still a solution. But the other curves are approaching it, and will not touch it.
So every curve approaches it, but only itself is touching it.
Yes. Okay, so then part F, show that, oh sorry, still writing.
Yeah, just the last one, it's fine, you can say it. Asymptotic to slide, yeah, that's
Show that y equals a e to the x minus 1 is a solution for all constants a. This is what we were doing in the last lesson. So those of you who've done the exercise will know how to do this. What we do is we test this by testing the left-hand side and the right-hand side. So the left-hand side of that equation is yeah, sorry, but I want to test it with the differential equation. So I'm testing it with, okay, so let's start that again. I want to test it with the y dash equals a e to the x minus 1. That's my differential equation, and I want to show that this equation works for that one. So the left-hand side of my differential equation is a y dash, right? And y dash for my equation that I'm giving you in part F, what's the derivative of that a e to the x minus 1? No. Yes, good. A e to the x. So derivative of a e to the x is still a e to the x. Derivative of the x is -1 and the constant disappears. Now we check our right-hand side, which is the a e to the x minus 1, right? So a e to the x is
we already did differential.
So this should be, sorry, there was y dash equals x plus y. I had the wrong equation. Okay, so the right-hand side is x plus y, which is x plus, and we replaced the y with our equation for y, which was a e to the x minus 1. And luckily for us, the x's cancel out, and we get the a e to the x take away 1 like we had for the left-hand side. So we've shown it works for the left-hand side and the right-hand side. We're not trying to solve it at this stage. That's all we wanted to do. We just wanted to show that it was a solution to the differential equation. So part G says, explain these equations in terms of the slope field, including the isocline. Now, if this is all dependent on the different values of A, right? That tells you what different type of curve we're going to have. If A was equal to 0, this is our first type. If A was equal to 0, then our equation, and I'm looking at that equation there, the y equals a to the x minus 1. If A was 0, that whole first term would disappear, and I would just have the isocline, I won't use that one because it's too thick. I would just have the isocline y equals minus x minus 1. So when a equals 0, that equation looks familiar. That was one of the lines that we drew on our curve, on our slope field. What happens when a is greater than 0? If a is greater than 0, that means we have got our a positive a e to the x, because a is positive a e to the x. What does that look like? Normally an exponential. It is a curve that goes upwards, right? So that is representing all of the curves that are related to exponentials that are curving upwards above that isocline. So it is the curves above y equals minus x minus 1 that curl upwards. And as you can probably guess, if we looked at when a was less than 0, you're then putting a negative in front of your exponential part. What do negative exponentials look like? You put them down. They curve downwards. They go below the y-axis. Obviously not perfect exponentials because you've still got the minus x minus 1, but that leading term is having a very big impact. So these are the curves. Yes. And we also know that all the curves are asymptotic to the y equals minus x minus 1. It is also interesting to note that if you were to do a limit if we're approaching negative infinity, because what was happening, all of those curves, as we were going, let me come back up here for a second. As we're going way out to the left, all of those curves are closing in on that isocline, right? They're closing in on that blue line. What are they all approaching? In terms of a gradient, if I do the limit as we're approaching negative infinity of my gradient, which was ae to the x minus 1, that was the gradient of my curve, that was my derivative of my curve that I have. How do you find a limit? If you put negative infinity into that x, e to a negative infinity, what is that basically equal to? 0. So that whole exponential part is basically equal to 0, which means that that limit would be approaching negative 1. All of those curves are coming up and approaching a gradient of negative 1 as they come and fall in line with that blue line that they were all approaching. Okay, we still have another one.
How do you do this one?
Then it's all based on the y. That's exactly. Yeah, that means that the x value is irrelevant. So for this one, you can see what Ben is talking about. The y dash equals, and that whole right-hand side of the equation is only in terms of y, which means you just sub in the y value. You sub in y is equal to minus 4. Let's type that in. You'd go quarter, just a sec, 4 minus 2 in brackets, and 4 plus 2. What do you get? No, you don't. No, you don't. Keep trying. 3, you get 3. But it means that it's not changing for the x values. It means every single one of those is going to be a 3 because doesn't matter what the x is doing, it's only ever the y value that we sub in. Sub in that y is equal to positive 3 now. No. 1.25 or 5 over 4. I left it as a fraction. So all of those are going to be 5 over 4, 5 over 4, the whole way down the line. The good news of these is it makes it much easier to draw because all the gradients are the same the whole way down. And 2, because look at one of those brackets, if you put 2 into that second bracket, what do you get? 0, which means all of these are zeros. Okay, sub in 1. And should I just tell you what it is to save time? We've been going for a while here. Negative 3/4. Then sub in 0, and you should get negative 1. Subbing in negative 1, you get a negative 3/4 again. Subbing in negative 2, again, that's going to make one of those brackets 0, which means they'll all be zeros again. Subbing in minus 3, we get 5 over 4. That's a bit messy. And then finally subbing in -4, we get 3. Okay, so drawing this. Okay, so starting with the top line of a gradient of, when y equals 4, we have a gradient of 3, which is quite steep. It's big, steep gradient of 3 the whole way along the line. Same gradient whole way down. Then we want a gradient of 5/4 or 1.25, so just slightly bigger than 45 degrees. Or about 45 degrees even. Then we have a gradient of 0. Then we go to negative gradients, -3/4, so that's negative 0.75, so just under a -1 slope. Just a little bit flatter. Then we have -1, so a little bit steeper for the -1. Then we're back to -3/4 again. So not a lot of change in gradient in there. Then at -2, we're back to 0 gradients. At -3, we're back to +1.25, so just over 45 degrees.
So that'd be like what tan looks like on the inside, but like
The inverse tan? Yeah, good one. Well done. And then 3 is a steep. Let me just finish this one. We'll come back. Let's just finish this off. So I want to make sure we're going to run out of time. In the middle, it does look a bit like the inverse tan, yes. Okay, so, but it's not. Anyway, we're not finding that. We don't have to find the equation for this one. So from the slope field, identify the constant solutions. Where do you think they are? What can you see? Some nice lines happening. Yes. So it's, and I'm assuming you meant y equals, because of course you did. Yeah, of course you did. When y equals 2 and y equals -2, because both of those have gradients of 0 the whole way through. Okay, so you'd see if we wanted to draw on here, we would have a line coming through there and another one through there. Okay, part C. Substitute into the differential equation to show that they are solutions. I've got to do that for both of them. So I'm going to divide my page here. So first of all, I'm going to show for when y is equal to the +2. If I substitute that into my equation, my differential equation, let's just go to the right-hand side first, because we have the y dash on the other side. On the right-hand side of my equation, I have got a quarter bracket. Then it was, where's my equation? Y minus 2, so it's going to be 2 minus 2, and then 2 plus 2. Now, because of that middle bracket, the 2 minus 2, that's where the 0 comes from, right? That is equal to 0. And what is the derivative or the gradient of 2? Like if you would differentiate, it'd be 0, right? So that is actually equal to the left-hand side, which means that that one is a solution. And you do the same thing to the other one, same process, and you get the same thing. So when you go when y equals -2, put that into the equation. If I put it into the right-hand side, I get quarter -2 minus 2, and then -2 plus 2, which of course is going to be equal to 0. The gradient of minus 2 is still 0, so that is equal to the left-hand side. So therefore, that one's a solution. This was from up here. So the left-hand side of my equation is y dash. Okay, what is the y dash or the gradient of an equation 2? It's just 0 because it's a constant. Yeah. All right, part D. If the horizontal axis is time, describe the behavior of the solution curves near these constant solutions and distinguish between them. Explaining questions, don't we love them? So first of all, because we're talking about time, time moves forward, meaning that we're going to be talking about our graphs as we move from left to right. So looking at this graph up here, we want to see what is happening as we go from left to right. Now, I didn't draw any other solution curves on there, did I? On above that y equals 2, we've got a 40, not 45, but almost 45 degree line. Then it increases to 3. And those gradients, if I were to keep going, they're going to get higher going up there. So above that line, these solution curves are going to be coming up like that. Okay, they're going to be coming down low to the 0. They're getting close to that 0 line. And then they'll be going up really steep. In between those two horizontal lines, we have a smaller negative slope, steep negative slope, back to the smaller negative slope. So this is that kind of curve going through there. And you would have multiples of them. You could move them up and down, right? But that's the general trend of all the curves that are between those two. I might draw another couple in there. We'd have another one coming down here. And they'd be coming down close and coming in close in there. Below that bottom horizontal line, we have negative gradients that are getting steeper as we go further down the y values. And they'd be getting shallower as they come up to the 0 gradients. Okay, so this is what we have to discuss. What is happening to these curves over time? So if we start on the left, what is happening? Let's have a look at the y equals negative 2 line. As you're moving from left to right, those curves that I've drawn, the further I go towards the right, all those curves are approaching that line, aren't they? Yeah. All right, that's point number 1. So, first point, for y equals negative 2, looking at that particular one, as time increases, the bottom curve approaches y equals minus 2. And we actually say that that's what we call, it's moving to an equilibrium. It's a word you might come across. I'll write that in brackets.
That's not okay.
Okay, so it's kind of balancing. It's coming in, it's approaching that, reaching an equilibrium. But for y equals the positive 2, let's go back and have a look at what's happening in our positive 2. On the left side, all my curves are quite close to that y equals positive 2, right? But as time is increasing, what is happening? They're going away, right? When you talk about the curve above, it is moving away quite quickly, going vertically. So it is increasing indefinitely. So any point with y greater than 2, so any of those ones above the y equals 2 are increasing indefinitely. Any point that is y value less than 2 is approaching, what is it approaching? the y equals negative 2. All those ones, they're starting up at y equals positive 2, but then they all, as time is passing, they're all going down and approaching that y is equal to negative 2. So we have special names for that. We say that y is equal to 2, that one at the top is what we call an unstable equilibrium, because any small change around that y value is going to send it off in different directions, right? Unstable. So any, sorry, let me write the unstable equilibrium part first. Is an unstable equilibrium because any small changes will see drastic consequences. So moving away drastically. Whereas the y equals negative 2, it is our stable equilibrium, because if we make changes to that, it's actually going to keep returning back to negative 2. Okay, that's it.